So the next speaker is Jesus. He will show us a test study about PCA analysis for absorption measurements correction schemes. So the floor is yours. Jesus.
Okay, thank you. First of all, since it was a test study, when we submitted the abstract, we thought about PCA and then we changed.
Oh.
So it's no longer PCA. Now it's, we just call it machine learning. Okay. Can I control? All right. So we will move from a very interesting for all topic, images, to a much more specific topic, which is measurement correction. Boring, I know, but very important, right? Because the correction of the data that we are measuring ultimately is an input to the absorption that the models are for climate models are using. So by constraining these measurements, we are improving a lot the climate outputs, and we know about the urgency of doing this, right? We don't need to be reminded of that. So we are interested mostly on aerosols. So when we think about climate warming, we think about CO2 because of methane and so on, and the gases because they are the most absorbing. But here we have our small light absorbing aerosols, and mostly VC, which, as we can see, also proves to be quite a warming agent in the atmosphere. And it's able to change the thermodynamics properties and to indirect or directly modify the atmosphere. Overall, its absorption is of 1.1 watts per square meter, which is not so distant from CO2, although the concentrations are very different. So we have to bear this in mind. So the main objective of this particular study is, since there is a lack of a reference absorption measurement well established across measurement networks, we want, based on a novel correction technique, to constrain this huge network we have across the world and improve these measurements. To do so, we have used this site-specific, we want to do site-specific corrections for this little ethalometer using this reference instrument, right? And we want to apply a machine learning model and test how well it works in compensating this data. To do so, first of all, we have used a small summer campaign over Granada, where we have only 3 months of data, but it's good enough. And we have the reference absorption measurement, the absorption from these filter photometers that are well established across all the networks around the world, and these collocated measurements that we want to constrain the model with to predict and forecast this and compensate this absorption from these filter photometers. So what is the problem? Why do we need to correct this data, you might think? So we need to correct it because these filter photometers that are widely deployed have this huge error when you reach a sinus scattering albedo of 1. And this, bear in mind, so that above 0.95, this is what most of the remote and background stations across Europe measure. So we are on the limit of the detection limit of not the detection limit, but when the artifact becomes too big. So we want to compensate this. And we can compensate this manually, like the traditional method, but to do so, we need the scattering. And not many stations have this scattering. Oh, furthermore, we also have the particle size that also somehow influences this through this penetration on the filter. So, blah, blah, we have this traditional approach, we can correct it, but then let's apply a machine learning algorithm to compensate when we don't have these collocated measurements to correct. How well could it work, right? Okay, so we have our tables, and as such, we thought maybe let's apply a multilinear regression to check if this, let's say, easier and simple method also works or not. And then we use a gradient Bushian ensemble of decision trees to, given the variable we want to compensate through different decision trees, compensate this data. So here we have our results, and basically we see that both multilinear, or maybe it's too small, I don't know. So maybe multilinear regression and gradient boosting, so blue and brownies, compensate quite well when compared against the non-correction data. And in particular, the gradient boosting, the machine learning model works very well, not so much as the multilinear regression, when we don't have this scattering data. When we have both parameters, both the size of the particles and the scattering, even the multilinear regression works well, which is great, because if we don't need it, then we can use just machine learning. But this special case of not having scattering is hugely important. So this proves to be something very meaningful. And then when we compare, we got very good results of almost a one-to-one correction, right? So then we do this analysis for other wavelength measurements where we have a higher signal-to-noise ratio, and we can still see that, okay, the correction is maybe not so good, but still it's quite good in comparison with not correcting. So we improve the baseline. So the future steps of our test study are to expand this analysis to every possible wavelength measurements we have within this data set, to check if the model is still able to compensate when we don't use as a reference measurement our reference instrument, but the manual correction. To then check over a broader database from across Europe to expand this analysis and check, okay, these networks do not have this reference measurement, but maybe we can do some tests where we manually correct the data and train the model on this manually corrected data, and then for a given net subset of stations, and then expand this model to the rest and check if it works and validate it. So now that would be great, because then everybody would be able to use this model to compensate the data, and ultimately this will go into the networks and into the measurements that are fed into the climate. So as a conclusion, we can tell that both multilinear regression and gradient boosting algorithms provide high quality compensations, although gradient boosting outperforms the multilinear regression when there is this lack of data. That is what we are most interested on anyway. And that we have to, given the good results, we want to extrapolate this to the rest of the networks. So thank you very much for your attention, and I think I'm
Thank you, Jesus. You're fast. Everyone likes that.
well,
So are there questions? Any questions?
Yeah, so very interesting, very nice talk. Just to understand a bit better, so traditionally these absorptions were done manually. I mean, absorption corrections, sorry. Or what is the state of the art? Like everybody's doing.
So the state of the art is the compensation can be manually done, but nobody does it because it requires to have the scattering and a good filter scattering signal, and that's rare abyss. So it's not so common, and we have to think about scale. Filter photometers probably are on a ratio of 10:1 to scattering measurements. So for each 10 stations where there is absorption, where there is 1 with the scattering. So we can not only compensate for this one station, that maybe somebody can then do it if he has the time or if he is willing to do it, but then for all of them and do it through a way that is easy for the user and the data provider to correct it. Yes.
Cool, nice, thank you.
Any other questions?
So
no.
I will ask you, Jesus, later anyway. But I just wanted to ask. So you have this tabulated data, right?
Yeah.
And then you either try the gradient boosting or you go with the multilinear regression.
Yeah.
I just wanted to ask: did you do any study on the correlation between the parameters? Maybe if some parameters are correlated, then you don't need a big decision tree.
Yes, so I have already, so yes, I did include it. We do this study, and the constraining variables I'm inputting already I am already filtering out any possible correlated variables, yes.
Any other questions? Okay, let's thank Jesus.
Thank you.